Yeah, maybe we should get started. So today we're very lucky to have Alex Maloney visiting all the way from Canada. So Alex, I guess you started in Harvard as a graduate student and then moved between Stanford and IAS before ending up in McGill several years ago. And today we'll hear about exciting developments in quantum gravity. So go for it.
All right. Well, thank you for the invitation. It's a great pleasure to be here, to come down south to Minnesota, where it is actually warmer here than it currently is in Montreal.
It's actually the same, latitude.
Is it the same latitude? I was wondering about that. Good. So I was told that I can take off my mask. I'm happy to do so. Would anyone prefer if I kept my mask on? I'm just fine to do that. We took a brief vote earlier and people seem to prefer unmasked. So that's what I'll go ahead and do. Good. So today I'm going to tell you a little bit about some work that I've been doing over the last year or so. The primary reference for what I'll be talking about is a paper I wrote with Edward Witten last summer. But of course, there's many things that can be said. I'll talk a little bit about a paper I wrote with my former student, Scott Collier at Princeton, as well as I might refer to some stuff written with these guys. And I should also mention a very nice paper of Afkami Jetty, Cohn Hartman, and Tajdini that articulated some of the ideas that I'll be talking about today, which they had been working on independently. And just also as a way of introduction, let me start by saying that I understand it's a reasonably broad audience here. I'll try and start with a very general overview, but I will get into some of the more technical aspects. But let me please encourage everyone to stop, interrupt, ask questions. I have no particular agenda about getting to a particular endpoint at the end of 60 minutes. So I'm very happy to be interrupted if anyone has any questions or wants any clarification. So I'd like to begin with a general overview. So my primary motivation is trying to understand quantum gravity. And one of the best tools that we have to understand quantum gravity is known as the ADS-CFT correspondence, which is a relationship between gravity in asymptotically anti-de Sitter space and a conformal field theory that lives in one less dimension. And this is an example of a duality, which we are quite familiar with in the study of quantum field theory, but one which is novel in that it relates a gravitational theory to a theory without gravity. But let me begin by telling you that when we think about ADS-CFT, we really think about this as an exact equivalence between two different quantum theories. So for example, that means that gravity in anti-de Sitter space is described by a Hilbert space and a Hamiltonian, much like in any other quantum mechanical theory. And this Hilbert space and Hamiltonian are, at least in the original formulations of ADS-CFT, supposed to be equal to the Hilbert space and the Hamiltonian of some quantum field theory, and in particular, a conformal field theory. And this correspondence has proven incredibly useful. It's taught us many deep things. For example, it's taught us about black hole entropy, which is one of my primary interests. It's taught us about the dynamics of strongly coupled gauge theories and their phase transitions. But one of the main drawbacks of the ADS-CFT correspondence, as it is usually formulated, is that because it is a strong weak coupling duality, you can almost never do exact computations on both sides of this duality at the same time. So it relates a strongly coupled theory to a weakly coupled theory. So for example, if you are studying semi-classical weakly coupled gravity in anti-de Sitter space, this would correspond to some strong coupling conformal field theory, where it's difficult to compute exactly. And on the other hand, a weakly coupled conformal field theory, where the usual tools of Feynman diagrams or other perturbative techniques are available, would correspond to some highly quantum theory of gravity in anti-de Sitter space. But there are certain examples where we can do exact computations. And when we do so, we find a surprise. So in particular, in certain models of quantum gravity, and here I'm referring to them as simple models because they're models where we can really compute in the gravitational theory exactly, what one finds is that gravity in ADS is not dual to a CFT, but rather to an average over many conformal field theories. And the picture that you should have in your head when you think about this is that each element of the ensemble is a conformal field theory, which could be interpreted as a UV complete theory of quantum gravity. And so this is a perfectly good theory of quantum gravity, but it is one that is very difficult to study. And in fact, it turns out that the ensemble is much, much easier to study and is the thing that corresponds to this simple model of gravity in anti-de Sitter space. And so we're drawing here a lot of inspiration from the study of disordered systems in condensed matter theory, where, for example, if you wanted to study a material which had very complicated dynamics, very complicated coupling constants, then it's very often the case that studying a particular material with very complicated coupling constants is a difficult thing to do. But if we treat the coupling constants as random variables, and you think not about a single instance of the Hamiltonian of the system with a particular set of coupling constants, but rather the ensemble of Hamiltonians with many coupling constants, then the ensemble averaged theory is much easier to study than any individual instance of the system. So for example, if one studies, say, a random coupling Ising model, then if the couplings are drawn from a distribution with a large enough variance, this is something that looks like a spin glass at low temperatures, then any individual spin glass is very difficult to study. But nevertheless, by considering the ensemble average of many such systems, you can find a tractable system that can be characterized in relatively simple terms.
Sorry, a question.
Yes, please.
Normally, the way it's formulated is gravity in ADS is just equal to just one CFT.
Correct.
So here you're going to generalize the usual prescription, is that correct?
So what I'm trying to say here is that indeed the standard formulation of the ADS CFT correspondence relates a theory of gravity to a conformal field theory. However, the standard formulations of ADS CFT all involve very fancy theories of gravity where we can't actually compute anything exactly. And it turns out to be the case that in any theory of gravity that I know of, where you can actually compute anything exactly on the quantum theory of gravity, it turns out to be that that theory of gravity is described not by a conformal field theory, but by many conformal field theories in a very precise sense, which I'll be talking about in more detail. There's an, please.
Your remark with regards to Ising model.
Yes.
Because Ising model is solvable, and we know all anomalous all dimensions of all of them.
I was referring, sorry.
So in which sense it is very complicated?
No, I was referring to, for example, a random coupling generalization of the Ising model, like the Sherrington-Kirkpatrick model or something like that, where you have not constant couplings, but you have some more complicated set of couplings that are random variables pulled from some distribution. So yeah, I shouldn't have referred. Yeah. So for example, that's a model you could think about, say, Sherrington-Kirkpatrick or Edwards-Anderson, where you have random coupling constants, and each individual instance of the system for particular values of the couplings is a very complicated system with a very complicated density of states, but it's very difficult to describe. And so instead, what we do is we develop an effective theory where you just treat those, you treat the coupling constants as stochastic variables, as random variables. And that provides a much more effective description of the system, and one which is much easier to study, but is sufficient to understand all but the most fine-grained observables. So for example, you're not going to reproduce the exact microstates, the exact discrete spectrum of the system by studying the ensemble average, but you will reproduce all, any sort of everything but the most fine-grained observables. And we'll talk about this quite explicitly in the theories that I'm going to try and study in more detail today.
But I'm actually condensed matter guy, and I'm dealing with disordered systems. And I don't understand you which real system we will describe in this way. So if I have spin mass with a say 1 over r cube and Ruderman-Kittel interaction, normal, how will I describe it by your method?
So what I'm going to do is describe very exactly what class of theories I'm going to study. So in particular, I'm not going to focus at the end of the day on things like random bond models, but instead I'll consider an ensemble of conformal field theories. So maybe what I can do is maybe if you'll wait and let me define exactly the model that I'm going to study,
So
then we can have.
You promise condensed matter example? You promise.
Well, so this is going.
Yeah. Do you promise condensed matter example of a realistic system?
I'll promise an example of conformal field theories that are of relevance to condensed matter physics. That is to say, I'll be studying ensembles of conformal field theories that have some relevance to condensed matter physics. In particular, I'll study, for example, free boson conformal field theories that we would use to describe a Luttinger liquid, for example. But the way that I'm going to be studying them may or may not be relevant for actual, condensed matter physics.
Okay, thank you.
Thank you. Great. Good. Any other questions? Great. So why don't I continue? So what I really want to do is develop a theory of random conformal field theories. So my inspiration here is random matrix theory. So for example, there's a very classic story that if we wish to understand the dynamics of a very complicated quantum mechanical system, then you could think of the Hamiltonian of the system as a Hermitian operator, and you could study an ensemble of random Hermitian matrices. Okay? And this has proven to be a very effective tool in the study of, for example, complicated dynamical systems. And what I'd really like to do is develop a theory of random quantum field theory, and in particular of random conformal field theory, that generalizes this notion of random matrix theory. So to do so, let me remind you, first of all, what is the data that defines a conformal field theory? So if I'm talking about the Hamiltonian of a quantum system, then that Hamiltonian is defined by its spectrum. A conformal field theory is similar in that to define a conformal field theory, we need a spectrum, okay? A spectrum, which in this case, if I'm considering a conformal field theory, would be a list of operator dimensions and spins. But conformal field theories and quantum field theories are more than just a spectrum. There are also coupling constants. And in the case of a conformal field theory, those coupling constants are packaged into some set of operator product expansion coefficients. These are basically the 3-point coupling constants in the theory. And so the program of developing a theory of random conformal field theory then would have 3 steps. The first is we should determine the allowed values of this data, the allowed spectra and OPE coefficients. The second is we should find a probability distribution over this space of data. The third is where we should compute some averages and compare, hopefully, to some kind of theory of gravity. Now, this is a very tall order. So for example, step 1 in this process has a name. It's called the conformal bootstrap problem, right? In particular, this is the problem of solving strongly coupled, oops, sorry, I hit a button there. This is the problem of solving strongly coupled conformal field theory to determine the space of CFTs. Even if you could carry out step 1 in this procedure in all generality, you would already be rich and famous because you would have essentially solved strongly coupled quantum field theory. So this is a very hard problem. So what I'm going to do is what we always do in physics when we have a problem we can't solve. I'm going to add symmetries until I can solve it. So in particular, the first thing that I'm going to do is, instead of considering CFTs in all generality, I'm going to consider CFTs in 2 dimensions, which would be related to theories of gravity in 3 dimensions. So such theories, quite famously, have a much stronger symmetry structure than conformal field theories in higher dimensions. In particular, in higher dimensions, the symmetries of a conformal field theory are those of the conformal group, SOD, 2. But for 2-dimensional CFTs, there's actually an infinite dimensional extension of this symmetry group, which is known as the Virasoro algebra. And so in some, but not all cases, this allows 2-dimensional CFTs to be solved exactly. 2-dimensional CFTs are generally characterized by a single dimensionless coupling constant, which is known as the central charge. This is the dimensionless quantity that describes the conformal anomaly in the theory. Roughly speaking, it is the dimensionless constant that tells you how this CFT reacts to the introduction of a length scale. It does things like determines the Casimir energy, the high energy density of states, and so forth. And the one piece of the ADS CFT dictionary that you need to know is that the central charge of a 2-dimensional conformal field theory is also a coupling constant on the gravity side. So in particular, if you're talking about gravity in anti-de Sitter space, ADS is a curved geometry that has a length scale that I've called L here. And Newton's constant in 2 + 1 dimensions also has dimensions of length. So the dimensionless coupling constant of a 3D theory of gravity is the ADS radius in Planck units, L/g. And that's equal to the central charge of the dual CFT. And if I didn't put my factors of the speed of light and h bar in there, but if I were to put them back in, then this central charge would be 1 over the h bar of the theory. So the semi-classical limit of a theory of gravity is one with large central charge, is a CFT with large central charge. Now, I said that in order to solve this problem, I needed to add symmetries. So I'm going to add as much symmetry as I can get away with. And so in particular, it turns out that the most symmetry you can add for some value of the central charge that I'll call n is a u1 to the n times u1 to the n symmetry. And typically in conformal field theory land in 2 dimensions, we describe symmetries in terms of an algebra of chiral operators. And so this symmetry is known as a u1 to the n times u1 to the n current algebra. And now it turns out that all 3 of the things that I wanted on the previous slide can be carried out explicitly for this class of CFTs with this specified symmetry algebra. I can solve the conformal bootstrap problem, and I'll find a finite dimensional space of conformal field theories.
One over n solution, because at large Virasoro,
There is, okay,
Virasoro
great.
central charges, you can expand.
Absolutely. So there is a large central charge. So there are many things we can say about the large central charge expansion of Virasoro. I am actually considering a much larger current algebra, which makes life much simpler. So I'm not going to need any of that large central charge stuff, but there are many, many things that we could talk about the large central charge expansion. But today my life is going to be much simpler, so I won't need to refer to much of that. Yes, please.
And is there like a free field realization of this?
That is exactly what I'm going to be talking about. So, good. So there is a finite dimensional space of such CFTs. There is a natural probability distribution on this space of CFTs. And quite remarkably, one can compute the average of an arbitrary observable over this space of conformal field theories. And when you do, you find a remarkable answer. Question?
Just to make sure.
Please.
N here Does it have to be large or? is it-
N does not actually have to be large. If we wish to interpret this as a semi-classical theory of gravity, N should be large because C is N and N is 1 over H bar, but it need not be large.
In particular, the statement.
Yeah.
About what we do with the CFT at home farm.
At the end of the day, the interpretation of this theory of gravity in a semi-classical limit is kind of subtle for reasons that I will mention if we get there. Good. Please.
Just to follow up on that
Mhm.
question, because you do have a number of colors in the CFT, which is large. Right?
Yes.
But that's not, obviously, it's not the same N here as the central charge. Right?
N is the central charge. Yes.
But it's the number of colors in the CFT.
Okay. So what I have a U1 to the N times a U1 to the N symmetry. What I don't have is a rotation symmetry that is going to rotate between my degrees of freedom. So what I don't have is an N squared global symmetry or gauge symmetry. These theories that I'm going to describe can, in a sense, be thought of as discrete gauge theories. And the average that I'll be talking about is an average over possible discrete gauge groups.
Okay, so it's not a continuous gauge theory. Right?
It is not a continuous gauge theory. It is best thought as a discrete gauge theory.
With this global symmetry.
Yeah, so these here should be regarded as global symmetries in the CFT. In the gravity theory, they will turn into gauge symmetries. And so the relevant gauge theory in the bulk is going to be closely related to a Chern-Simons theory based on this gauge group. Good. Thank you. Great questions. Good. So in particular, what we're going to discover is that if you take this family of CFTs and you average over it with the particular probability distribution that I'll argue is the only natural one, you find something that can be interpreted as a theory of gravity. And what do I mean by that exactly? Well, a theory of gravity is something that I should be able to study using a path integral, where I sum over all geometries weighted by a Euclidean action. Now, of course, in general, we don't know how to compute Euclidean path integrals exactly in a quantum field theory, much less in a theory of gravity. So what do I mean when I write down an expression like this? Well, let's think about how we would start computing such a path integral. We would start by doing a saddle point expansion, where I sum over solutions to the classical equations of motion, weighted by a classical action. And then if you're very powerful, you would compute a one-loop correction. And then if you and/or your graduate students are even more powerful, you would compute a two-loop correction, and so on and so forth. And now, if you are lucky enough to have a theory where you can find all of the solutions to the equations of motion, and you can compute the infinite series of perturbative corrections around each solution to the equations of motion, then if you sum them up, that will give you the exact value of the path integral.
So in a usual before that lesson where people just naively quantize gravity and do the loop corrections like at this second loop,
Yeah.
into problems
Yes.
with UV completion and so
So,
on, right?
Indeed.
So here it's understood that
Here, this is
there is a nice UV completion.
here, everything is understood in the sense that I can find all of the solutions of the equations of motion. So we're in Euclidean signature, so those are interpreted as instantons. So I can find all the solutions of the equations of motion. I can compute the infinite series of corrections around each solution. You're going to be a little disappointed when I tell you how. It's because it turns out that they're all one loop exact. So in particular, there are no higher loop corrections. Okay. But nevertheless, I can find the infinite set of instantons. I can find the quantum corrections. I can sum them up, and I get exactly this answer for the average over a space of CFTs.
And the Stokes phenomena are all understood, so you know how to.
There are no Stokes phenomena.
There are
in
no
this case.
Stokes.
Stokes phenomena,
All
I
right,
mean,
the series all truncate. Okay.
right. If like, so a normal person would say, well, but Alex, this is supposed to be an asymptotic series. And that means that everything is some complicated function of your coupling constants that may have some fancy analytic structure. And I have to say words like Stokes phenomena and Borel summation and trans series and stuff like that. this is a much simpler theory. And this is both this is both the price that we pay and the benefit of assuming as much symmetry as possible. Because I got a theory that I could solve exactly, in the sense that I have a gravitational path integral that I can compute exactly. But the only reason I can compute it exactly is that it is a relatively simple theory where I don't have to deal with asymptotic series, for example. Although there's much more that could be said about it. Yeah. So in particular, these are theories of gravity in one less dimension, where many of the subtleties that arise when one tries to normalize theories of gravity are much easier to deal with. Yeah. Good. Great. Okay. So this was all a sort of general introduction. And what I'd like to do is then proceed by telling you a little bit about how one averages over spaces of CFTs. And then I'll talk a bit more about its gravitational interpretation and how we can interpret the result of this average of CFTs, in a sense, as a way involving a sum over black holes. And then at the end, if we have time, I'll talk about a little more, some interesting features of this. I'll talk about how these are related to wormholes and how we can use this to understand the spectral statistics of the theory. And then I'll end with some speculations, and instead of conclusions, I'll end with some confusions. Okay, we get there. Good. And again, I have no particular agenda, so I'm happy to be interrupted at any point as we proceed. But let's start with a very simple warm-up. So let's start by considering n is equal to 1. So here I'm looking for a theory with C equals 1 and a U1 times U1 current algebra. So what are those theories? Those theories are free bosons, okay? So here I'm just looking at a theory of a single free boson in 2 dimensions. Now I want a theory which has a discrete spectrum, okay? Which means that I need to take a compact boson. So my field X is a periodic variable. And there is a one-dimensional space of such theories that is labeled by the radius of that free boson. So these free boson CFTs are what we use when we talk about Luttinger liquids. And this radius is related to what's known as the Luttinger parameter of that family of theories. And this radius is to be thought of as a coordinate on the space of such theories. So the space of such theories that n equals 1 is one-dimensional, and R is a coordinate on the space of such theories. Now, how could I think about averaging over such theories? Well, to average over such theories, I should integrate over the space that I have called M1 here, which has a coordinate R. And it turns out that there is a very natural metric on this space. So there are many different ways of understanding this metric, but I'll actually tell you one easy way of understanding it that I didn't put on this slide. One way of understanding it is to remember that this free boson CFT has a very simple property known as T-duality, which means that the theory at radius R is the same as the theory at radius 1 over R. So let's now try and write down a metric on this space of theories. And we have to demand that it's invariant under R goes to 1 over R.
Over the Planck length or?
No, so R is a.
Oh, it's a dimensionless.
Yeah, R is dimensionless. So, this is just, there's no gravity. Gravity has made no appearance on this slide. This is just a CFT of a free boson of some radius R. And it is a fact of quantum field theory that the theory is invariant under R goes to 1 over R. And so if you were to write down a metric and you tried to demand that it was invariant under R goes to 1 over R, then you would quickly decide that this is the only sensible metric to write down. And so when I talk about so I now have a geometry on the space of quantum field theories defined by that metric. And when I talk about a probability distribution on the space of theories, the most natural one to use is just the measure associated with this metric, dr over R. So when I talk about averaging over the space of theories, I want to integrate with respect to R with the measure dr over R. I want to integrate from 1 to infinity, not 0 to infinity, because I don't want to double count my theories, because R and 1 over R define the same theory. Okay. So what sort of things would I like to compute? Well, you can imagine trying to compute the spectrum of the theory. So the spectrum of the theory is captured by the finite temperature partition function. So this is the sort of thing that we would like to average over the space of theories. So here, the finite temperature partition function is a function of R, the radius of my free boson, and beta, an inverse temperature. And it's easy to compute. Why is it easy to compute? It's easy to compute because it's a free theory. Okay. And in particular, in any free theory, you can compute the partition function of the theory because it's one loop exact, right? So it's just given by some sort of one loop determinant. And it's a straightforward exercise to go ahead and compute that one loop determinant. It basically sums over the oscillator modes of that free boson. There's one slight wrinkle to this, which is that they're actually, because we're working in Euclidean signature, an infinite set of classical solutions as well. Because now we're thinking about space being a circle and Euclidean time also being a circle of length equal to the inverse temperature. And so we have classical solutions that come from the ways that the field X can wind around as you go around either the spatial circle or the Euclidean time circle. So you have an infinite set of classical solutions, and it's an easy exercise to go ahead and write down the contribution to the partition function coming from that sum over classical solutions. I've done it here. It's what mathematicians would call a theta function. Okay, so that's great. I have the spectrum of the theory. I have a space of theories. I have a measure on the space of theories. So you could ask, what is the average spectrum of a free boson? This would be a little bit like asking, what is the average spectrum of a Hamiltonian integrated over some space of Hamiltonians? The answer, however, is something that you could have already guessed from my last slide. It's infinity, because I'm integrating dr over R from 1 to infinity. Okay. So at this point, you might throw up your hands and say, all of this makes no sense. We should just give up and go home. But it turns out that that infinity is an artifact of the fact that I considered only one free boson. And that if you consider many free bosons, then you get a much more interesting answer. So if you considered instead n free bosons, then the most general action that you could write down is the one that I've written here. So here I'm taking all my free bosons just to be periodic. They live on a circle. And it's a free theory, so the action is quadratic. And if you think about it, the most general action you can write down involves a symmetric n by n matrix that I have called G, and an anti-symmetric n by n matrix that I have called B. So these G and B are the coupling constants of the theory. There are n squared of them. And together they parameterize the n squared dimensional space of such conformal field theories. It turns out that this space of conformal field theories has a natural group theoretic structure. I won't go into it into too much detail, except to say that this space of CFTs happens to be a homogeneous space. Okay? And because of that, there is essentially a unique metric associated with it that respects the symmetries of the space of theories. So in particular, there is a T-duality symmetry, which is now an infinite set of symmetries that generalize that R to 1 over R symmetry that I wrote down earlier. And there is a natural metric you can write down that respects those symmetries. And when I talk about averaging over this space of theories, what I mean is averaging over the space of CFTs with this measure. And the important difference from what I described on the previous slide is that now this is a space with finite volume. So I can really normalize it and think of it as a genuine probability distribution. Previously, when I had that dr over r measure, that was a non-normalizable probability distribution. So I couldn't really even honestly think about it as a
So
probability
is n
distribution.
equals 1 as a special point?
N equals 1 is a special case where I can't really define a normalizable probability distribution on the space of theories, at least not one that respects this symmetry.
For 2 it's already fine.
For 2, it's already fine. Great. So when I talk about averaging over the space of CFTs, I literally mean doing an integral, where I'm integrating over a space of conformal field theories, a finite dimensional space with a particular measure. Now, I'll mention one comment, which is that a free boson in 1 + 1 dimensions also can be thought of as a fermionic theory. So there's this famous relation between bosons and fermions in 2 dimensions, where a theory of a single free boson can be mapped to a theory of interacting fermions with 4 Fermi interactions. And the radius of the free boson corresponds to the 4 Fermi coupling. So you can think about this space of CFTs also in a fermionic language, where I'm integrating over a space of 4 Fermi couplings in a 2D CFT. So for those of you who've studied the SYK model, which is a model of interacting fermions in 1 less dimension, what one does there is one integrates over a space of 4 Fermi couplings in order to define some sort of disordered theory. And this can really be regarded as a version of the SYK model in 1 higher dimension. The most interesting difference being that in SYK, one just takes, for example, a Gaussian distribution on the space of couplings. Whereas here, we have a group theoretic structure, which is picking out a different, unique, and very specific measure on the space of 4 Fermi couplings. And it's not one that you would just guess if you were to look at the 4 Fermi coupling. It's one that's picked out by the duality invariance of the theory. Okay. Yes, please.
The B's in terms of the fermions, those are also full fermions?
They are. They're ones that mix. So they only exist if you have more than 1 boson. So you'd need at least 4 fermions. Okay. And so there's some more complicated mixture between those fermions. Good. Great. So I've defined now a space of CFTs. I've defined a probability distribution on my space of CFTs. Let's compute an average. So the spectrum, again, would be encoded in a finite temperature partition function. So for any individual instance of this ensemble, for any particular free boson theory, so I've labeled them by a coordinate m. Little m is a coordinate on the space of theories. You can go ahead and compute the partition function. Again, it's a free theory. It's not so hard. It involves a 1-loop determinant, basically the same one I showed you earlier, and a sum over classical solutions. More complicated, but I'm not going to write it down for you. And then it turns out that we can compute the average over the space of CFTs. And when I say we, I mean we as a species, because it was the mathematician Siegel who, for reasons of his own, trying to solve certain problems in number theory, first described the method by which such averages can be computed. Interestingly enough, if you try and read the proofs of this formula in the number theory literature, they're quite incomprehensible. They involve things called the Adels, which unfortunately is not a singer, but something to do with chaotic numbers. I personally found them a little impenetrable, but we managed to find proofs of these formulas that I think are much more closely inspired by physics, that if you're interested, I could describe to you pretty easily afterwards. Basically, the point, however, is that this 1-loop determinant goes along for the ride. And what we're left here is a particular function of the inverse temperature that I have written in this interesting way here. The idea is that we are computing a partition function of the theory on the torus. And the answer that we get involves a sum over what is known as the modular group of the torus. So for those of you who have not studied it, it's really nothing particularly fancy. The idea is that if you have a torus here, let's say I have a torus where space is length 1 and Euclidean time is length beta, then if you're studying a conformal field theory on this torus, you could always do a 45-degree rotation to write it as a space of length beta and Euclidean time of length 1, and then a conformal transformation to rescale by beta. And you would see that, in fact, up to a conformal transformation, a torus with a Euclidean time circle of length beta is the same as one with Euclidean time circle of length 1 over beta. So this is an example of a modular transformation. It is a symmetry of Euclidean field theories in 2 dimensions on a torus. And this modular group describes the group of such symmetries. And so what we have here is an expression for the average partition function that is given by the sum over such symmetries. So the symmetry that I've drawn here is one of them. It's the one that takes beta to 1 over beta. In terms of this SL2Z matrix here, it's the one with 0, 1, 1, 0. And it is just one example of an infinite number of such symmetries. And in some sense, you could have guessed this formula based on the symmetries of the theory, but I won't get into too much more detail. And so here I've just described the formula for you for a torus, but it turns out that we can compute the average of essentially any observable in the theory in a similar way. The partition function on any surface, not just a torus. Yes.
It looks like the average is modular invariant, is that right?
Indeed,
Okay.
indeed.
But the starting point is not quite, right? The T transformations won't be the.
The starting point is modular. Yeah. So
You didn't have the sum over boundary conditions?
okay.
The
No,
theta function is not modular, right? It's modular. It has transformations that are T.
this is also not modular invariant.
Uh-huh.
The numerator and the denominator both transform like modular forms in such a way that the total partition function is modular invariant.
Okay.
Yeah, I mean, it turns out on a general surface, it's not modular invariant, but it transforms like the section of some line bundle in some fancy way that maybe is not too useful to talk about. Okay, thank you right now. Great, thank you. Good. Okay, so what's the gravity interpretation of all this? Okay, so I said I was computing torus partition functions. So let's think about how we could compute a torus partition function in a theory of gravity in ADS. Now, this is going to be a 3-dimensional theory of gravity, which means it's a theory where we have a metric, and the statement that it's the torus partition function means that I want to find a 3-dimensional geometry whose boundary is a torus. So let's think about how we could do that. So first of all, let's think about ADS3. So here I've written down the metric on ADS3 in Lorentzian signature. It's got a time coordinate, it's got an angular coordinate, and it's got a radial coordinate. And the way that you should think about this is that this is a 3-dimensional geometry that you should think of as a solid cylinder. So the time direction runs vertically, phi is an angular coordinate, and r is some radial coordinate that fills this in to make a solid cylinder. That's the Lorentzian signature metric. If I wanted to find a Euclidean metric, I would just flip the sign of this term here, and then I would get a metric on a cylinder in Euclidean signature. And if I wanted something whose boundary was a torus rather than a cylinder, I would just periodically identify Euclidean time. So one geometry that you would imagine contributes to the partition function of the theory on a torus is this geometry where I periodically identify in Euclidean time. So that is a geometry that has the topology of a solid donut, right? Because I started out with a cylinder and then I periodically identify in Euclidean time. So I glue the bottom of the cylinder to the top of the cylinder and I get a solid donut. But of course, that geometry has a name, okay? It's what we would call thermal anti-de Sitter space. What do I mean by that? What I mean is that when you periodically identify in Euclidean time, you're computing thermal quantities. So this is the geometry that you would study if you wanted to study finite temperature field theory in anti-de Sitter space. Okay. So what does such a thermal partition function do? Well, it counts degrees of freedom. And so the first thing we need to do is decide what are the perturbative degrees of freedom of the theory. Well, we started out with a boundary theory that had this large algebra of global symmetries. One of the ingredients of the ADS-CFT correspondence is that every global symmetry in the boundary corresponds to a gauge symmetry in the interior. So our bulk theory of gravity should include a gauge theory based on that gauge group. And indeed, this is just about the simplest kind of gauge theory that you could imagine. In particular, it's a Chern-Simons theory on the gauge group of U1 to some power. And these are going to be the only perturbative degrees of freedom. So our perturbative degrees of freedom are incredibly simple. They're just a bunch of free Chern-Simons gauge fields. And in particular, one of the things that I'm not going to include is a separate Einstein-Hilbert term. And in particular, there's a very specific sense that we can talk about in more detail if you like, in which, although we don't have a separate Einstein-Hilbert term, there is a sense in which it is induced at one loop. Because we have a bunch of gauge fields, what they more or less do is build up a composite graviton out of those perturbative gauge fields. There's some subtleties with that analysis, and we have to really think carefully about what we mean by that. But the basic idea is that in a two-dimensional CFT, or in any CFT, the stress tensor of the theory is the thing that couples to gravitons in ADS. Okay? But in these CFTs with this huge algebra of symmetries, the stress tensor is a composite operator that is built out of the currents of the theory that generate these U1 symmetries. And so correspondingly in the bulk, we think of the graviton as a composite operator built out of gauge fields. It is in this sense in which this theory is much simpler and rather different from a general theory of gravity based on, say, the Einstein action and independent graviton fields. Yes, please.
This Chern-Simons theory under a gauge transformation with anomalies on the ground.
Yeah, this is exactly the point. Like, we'll get back to this in just 1 second. So that is indeed that is what this Chern-Simons theory is going to do for us, basically.
And then this composite graviton, I mean, because it's gravity 3D, right? It's not.
So
it's a scalar field.
Well, so general relativity in 2+1 dimensions is a much different theory from general relativity in higher dimensions. In particular, even general relativity in 2+1 dimensions has no local degrees of freedom. So there are no propagating gravity waves in 2+1 dimensional gravity. Indeed, general relativity can, at the level of perturbation theory in 2+1 dimensions, be rewritten in terms of a Chern-Simons theory. Turns out to be an SL2R Chern-Simons theory, an SO31 Chern-Simons theory. This is now just an even simpler version of gravity where the metric comes from a U1 Chern-Simons theory instead of that Chern-Simons theory with a non-compact gauge group. Okay. It's a kind of special trick that you can pull in this low number of dimensions. Great. So just to articulate this a little bit more clearly, thermal ADS was a solid donut. So here I've tried to draw a picture of that donut here. And it's a straightforward exercise. It's a pretty easy exercise to go ahead and compute the partition function of some Chern-Simons gauge fields in this background. And I don't want to dwell on the answer, but just tell you that the answer is exactly what you expect. So there's a little bit of it's a little non-trivial. You know, Chern-Simons gauge theories have no local degrees of freedom. So if you were to compute the partition function by computing a one-loop determinant, you might say that there's nothing to do because there's no local degrees of freedom. But you have to be a little careful when you say that. And the reason is that when we say there's no local degrees of freedom, we mean that all of the degrees of freedom can be removed by a gauge transformation. But when you compute a one-loop determinant, you'll have a determinant acting on spin one fields, and then you'll have some Fadeev pop-up ghosts that come from the gauge fixing procedure. And when we say that there's no local degrees of freedom, that means that we say that these two things should cancel out. And it turns out that in Chern-Simons theory, they do cancel out almost. These are three-dimensional one-loop determinants, and they cancel out up to a two-dimensional piece that lives at the boundary. And this gets to the question that was asked earlier. And what is that two-dimensional piece that lives at the boundary? It is, oops, sorry, I'm going forward rather than backwards. The two-dimensional piece that lives at the boundary is exactly one of the terms that appeared in our sum. So it was the square root of beta over this free boson one-loop determinant. So what we've discovered is that, oops, the one-loop determinant gives us one of the terms that we discovered in this average over the space of CMT. What about the other terms? Well, the theory of gravity should include a sum over geometries. I told you about one of the geometries, the geometry that I called thermal ADS. And how is that geometry defined? Let's look at it. That geometry was defined by taking the solid cylinder and periodically identifying a Euclidean time. So what feature does that geometry have? Well, the feature that it has is that this circle, the phi circle, is contractible in the bulk, right? I can just, contract it to a point inside the bulk. But the Euclidean time circle is not contractible. So if you think about that, that means that if you started with an abstract torus like this, and you said, well, let's find a geometry whose boundary is that torus, this is one of those geometries. And the geometry is defined by this cycle being contractible in the interior and this one not being contractible. So that means that we've made a choice when we wrote down that geometry. We made a choice of which cycle was contractible. And it turns out that there are an infinite number of other such choices that you could make, where an arbitrary linear combination of the Euclidean time and spatial circle is contractible. So there are an infinite number of geometries that can contribute to this sum. And they are labeled by pairs of integers, C and D, which specify which cycle is contractible. So if you have an infinite number of different saddle points, that is to say an infinite number of different instantons, you should sum over them. And by the way, these geometries have a very clear physical interpretation. For example, let's think about the geometry where the Euclidean time cycle is contractible. What does it mean for the Euclidean time cycle to be contractible? It means there's a location in the geometry where the coefficient of dt squared goes to 0. So if you were in Lorentzian signature, what would you call a place where the coefficient of dt squared goes to 0? You would call it an event horizon. Okay. So these geometries are precisely black holes. And what we're doing here is summing over black holes. And in fact, this classification of geometries is precisely the same as the sum that appeared in this formula for the average partition function. In particular, I summed over this group SL2Z. This group SL2Z is labeled by 2x2 matrices with integer elements, and the lower two elements, C and D, are exactly the things that we sum over when we do this sum over geometries. And so at this point, I've given you all of the ingredients, but basically the conclusion is that from this calculation, the averaged partition function, averaged over the space of CFTs, has an interpretation as a sum over geometries, an infinite sum, but a sum that we can do, I wrote it down for you earlier, of a perturbative partition function with a classical and a one loop piece. And that was this U1 times U1 Chern-Simons partition function interpreted as a partition function of perturbative degrees of freedom. Now, I've computed for you here only the average of the simplest observable, trace e to the minus beta h. But remarkably enough, this works for any observable. Okay. So in particular, you could take the partition. So this is a very exciting formula, not least because I figured out how to put figures, hand-drawn figures as parts of the formula. But it's also an exciting formula because it describes the average of an arbitrary observable in the space of conformal field. And in 2D CFT land, by an arbitrary observable would mean the partition function on an arbitrary surface. So you could take the partition function on an arbitrary surface, average over the space of CFTs, and it is related to the sum over ways that you can fill in the surface with some three-dimensional geometry of a one loop piece with a classical piece with a one loop correction. Now, in the case where I have a general surface here, it turns out that you can't actually write down simple analytic closed form expressions for things like the one loop determinants appearing, but you can nevertheless show that they are exactly the things that arise. And similarly, although it is a much more complicated, you can't write down formulas for the sum over geometries that are nearly as explicit as what I wrote down earlier, but nevertheless, the exact same story holds. So this average over a space of CFTs is interpreted as a gravity path integral, including a sum over geometries, all of which we can write down, and a set of perturbative corrections, all of which we can compute. So this is the basic story. I'm just about out of time. So let me just end with one or two final comments. One comment I'll make is that because I'm averaging over spaces of conformal field theories, correlation functions do not factorize. Right? That is, so here I remind you this angular bracket means an ensemble average over a space of field theories with a probability distribution. What probability distributions do for a living is give you correlation functions that don't factorize. If correlation functions factorize, then that just means you have a delta function probability distribution. Correlation functions that don't factorize mean that you have some sort of variance or covariance in your probability distribution. And the geometric interpretation of this covariance, so here I've written the covariance of the partition function or the density of states in my theory. It's interpreted in the gravitational language as coming from Euclidean wormholes. And it is indeed these wormholes that are a signature of the probabilistic nature of this theory of gravity.
I'm sorry, but we have a class here at this time.
Okay, yes. So
We should wrap up.
yeah, so why don't I wrap up? So these wormholes are a signature of this theory being probabilistic. And indeed, one can compute the level statistics. So this is the quantity that you compute that is related to the density-density correlation functions in the theory. And it's something that is neither Poisson statistics nor random matrix statistics, but rather something in between. So I think this is probably a good place for me to conclude. So I'll stop there and we can maybe take the questions outside since there's a class here right now. Thank you.